Hi everyone, this is Mr. Lim and this is our fifth video on equilibrium graphs. So let's jump into it. Okay, so we're going to be looking at reaction rate graphs and concentration graphs. And please learn that these are two different things and that you have to really think to work out which one is the one that you're dealing with in the question, and so therefore choose the right considerations when drawing them. Okay, so please don't get confused by which is which. All right, so let's have a look. Okay, so reaction rate graphs. Describe what a reaction rate graph shows. What do you want to show? You want to show the forward and the reverse rates of reactions over some sort of time period. Okay, so the y-axis is rate of reaction, the x-axis is time. They change over time until they become equal. So if you think about it, they become equal because we're talking about equilibrium when forward rate of reaction is equal to the reverse rate of reaction. Okay, and here's one I prepared earlier, right? So as we said before, rate of reaction over here, time over here, okay? And then let's go through some of the other characteristics. Okay, so don't forget, if you ever do this, probably need a unit here. So this might be moles per liter per second, okay, because it's the rate of reaction, and time maybe in seconds or something. All right, actually probably not even rate of reaction. Actually, no, yeah, that's fine. Yep, okay, cool. So let's have a look at what else is here. Okay, so what does it show? Generally, changes in rate are greater the further away they are from the time when equilibrium is established. So the changes in rate greater when they are further away from when equilibrium is established. Okay, so they curve more and then they gradually flatten out. So let's have a look. Here's our graph. I got a forward and reverse reaction, and you can see that at the forward reaction started off at a certain value and the reverse reaction started off at 0, which means there was probably no products and lots of reactants there. Okay, so as the reactants reacted, the forward rate of reaction decreased at the beginning. Why? Because you have a lower concentration over time because the reactions are occurring. Okay, and this is increasing over time due to an increase in concentration. Okay, so the reverse increases, the forward decreases until they become equal, and then you have dynamic equilibrium. Okay, so dynamic equilibrium is when they're equal. Okay, so what does that mean? Dynamic equilibrium is when the two rates of reactions overlap. Okay, the two rates of reaction overlap. And therefore, that's when you know that there is dynamic equilibrium, because the equilibriums are effectively going at the same rate, both reaction rates. Okay, let's have a look at concentration graphs this time. Okay, so concentration graph shows the concentration of some or all of the chemical species over time. Okay, which ones do we get rid of in a chemical in an equilibrium system? Remember, because we're talking about some, so there's no solid or liquid. Okay, the y-axis is concentration or partial pressure, and the x-equilibrium is x-axis is time, and it changes over time, but as different to the reaction rates, they do not have to be equal at equilibrium. Okay, so here's one I prepared earlier. Again, concentration in moles per liter, right? Not moles per liter per second, which is the rate of reaction one, and over time. Okay, so let's move back. Okay, so what happens? Generally changes in the concentration of a species is greater further away from the time. Okay, so the concentration changes in concentration is the greatest when it's further away from when the equilibrium is established, which means you have a large curve at the beginning and low curve at the end when you start having the two rates of reaction equal. Okay, you also need to consider, this is really important when things change, they change by stoichiometric ratios. which means you have to consider the amount changing for each. So let's have a look over here in our example. All right, we have here A, B, and C, and we have here what? We have that A changed by X, B changed by 2X, and C changed by X as well. Which means if we are writing this out, this will be A, this will be B, because they are both reactants, because that's what they start with, and then I have C on the end. Okay, the B coefficient has to be larger than the other two by a factor of 2, so you've got a 2 there, and then you'll have a 1 or a blank space here, and then you'll have a 1 and a blank space here, or a blank space there. Okay, so the idea is that you have to take into account stoichiometry as they change. Then they're also going to change in stoichiometric amounts with their products, and also be consumed in stoichiometric ratio to the thing that is selling it. Right? So making sure that you check the stoichiometric ratios when drawing a concentration graph. And then finally, identify dynamic equilibrium on a concentration graph. How do you do that? That's when all of the concentrations stop changing. Therefore, you have dynamic equilibrium. Okay, when all the things stop changing, and they all start at the same time is when equilibrium is established. Okay, the idea is that whenever all of them stop changing concentrations, that's the start of the equilibrium system. Okay, so here we go. Dynamic equilibrium is when the concentrations of the chemical species are constant over a period of time. Okay, so what does that mean? Do I write it down here? No. Okay, so dynamic equilibrium on concentration graphs determines the chemical species over a period of time, and if one of those species was colored, you'd be able to say what color it was at that time. So let's just say A, B, and C. Let's just say that C is colorless. Colorless. And B is a brown substance. Okay, and let's just say A is colorless as well. If this one and if A and B are together, they're colorless and brown, which means you start off with brown, and then you let them react. At some point, you're going to have equilibrium system established, and if it was equilibrium system established with a high K, you would have lots of products and not many reactants, which so all of the brown substance would go. Okay, so that's the idea, that you can tell how much of a substance there is at the end of it from a concentration time graph. The idea that in this particular case, it would start off with a brown mixture, and then it would slowly get less and less brown. Okay, and that is it. So that's what we just talked about. We can infer K values from where their relative positions are. So where's that diagram? Where is it again? Okay, here I would say that the reactant's value is still fairly large and the product's value is still very small. So therefore, the K value might be quite a small value. All right. Yeah, so more reactants than products. A low K value, more reactants and more products than reactants, a high K value, and you can see that from the concentration graph. Then tips on drawing, really start with the end in mind. So when you draw a line, okay, you know that it has to go from here to somewhere here. It has to go up, so therefore that goes there, right? So start with the end in mind. Know where you're going to end. Know your curves. It is this curve. This is the right curve. Not something like that. That's the wrong curve, right? And this is also the wrong curve because that's not even a curve. Okay, so know your curves. Think about spikes. We're going to be going into what happens in concentration time graphs and rates of reaction times graphs, and suddenly you can have a spike and something will happen. All right. So think about spikes. You'll be learning about those more in the next couple of lessons. And always use a ruler. When it's at equilibrium, use a ruler. Okay, otherwise you're not going to show that you understand what's going on. Right, and that's it.